Welcome to the lecture on problem solving on getting design and rising methods. So, in this lecture we have to discuss about different types of problems which we need to solve, which are related to getting design and also rising design. So, in the getting design problems we will have the problems related to pouring and also some problems related to how the aspiration has to be prevented. So, those conditions are to be met. For that you have the different type of problems, and then in the rising you will have different rising methods we have discussed. So, we will discuss how to find the riser volume. Let us come to the first problem. The first problem is that a down sprue of 180 mm length has a diameter of 20 mm at its top end. So, you have the down sprue, and also the liquid metal in the pouring cup is maintained up to 60 mm height. So, the first problem is that you have a pouring cup and you have a down sprue, and this is the pouring cup height, and this pouring cup height is maintained as 60 mm, and the down sprue is of length 180 mm. So, this length is 180 mm. So, then what should be the diameter of the down sprue at its lower end to avoid aspiration? So, basically as you know that we define 0.1, 0.2 and 0.3. So, this height is h2, and this is known as hc, this is 60 mm. And so, what we see is that R is A3 by A2, that is basically under root SC by HT. So, HT is this total height, and you have to find the, so this value is given, the diameter of 20 mm at its top end. So, here A2 is given as 20 mm. Now, you have to find the diameter at the lower end. So, you have to find A3. This is A3, here the area is A3 and here the area is A2. So, we know that for avoiding the aspiration, the condition is that A3 by A2 has to be under root HC upon HT, and HT is nothing but HC plus H2. So, you will have HT as HC plus H2, that is 60 plus 180, so 240 mm. So, you will get SC as 60 and ST as 240. So, that is 1 by 2 and A3 by A2. So, you have to find the diameter. A3 will be D3 square and A2 will be D2 square. See, this is A3, this is not A2 basically, this is your D2. D2 is given, so you can find A2. The diameter is given, not the area. You have to find basically D3. So, once you know D3, you will find the A3. Now, so this D3 by D2 square will be 1 by 2. So, D3 will be D2 by root 2. So, D2 root 2 by 2. So, you will have once you know D2, you will find the values of D3, and that comes out to be D2 20 into root 2 by 2. So, 10 root 2, that is 14.15. So, 14.15 mm should be the diameter at the bottom end of the sprue, so that there is no aspiration. This is how you can solve this problem. The next problem is related to the again the pouring. A mold of dimension 60 centimeter by 30 centimeter or 40 centimeter is to be filled by liquid metal using top pouring method. You have the liquid metal height above the top surface of the mold as 14 centimeter and area of the gate is given as 6 centimeter square. Find the time taken to fill the mold. Also find the time taken when the mold is filled using bottom pouring, the height of liquid metal in the vertical column being the same. So, you have a mold of dimension 60 by 30 by 14. In one case you are pouring by top pouring, and in that top pouring the liquid metal height above top surface is 14 centimeter. So, you have two cases. You will have this is how your casting will look like, or you can have proper other way. So, what you see is you will have, so this height is given as 14 centimeter, this is 14 centimeter, and also this height is 14 centimeter, and here you will have the dimension that is given as 60 by 30. So, this is 60 and this is 30. So, this is one case of top pouring. Another case will be because this height comes out here. So, in that case what will happen? So, in that case basically this 14 centimeter height comes here and there is a case of bottom pouring. So, your liquid column height will be maximum here and this way it will be fed. So, this comes out of this height itself. So, this is 14 and also this is 14, and then you have this as 60 centimeter and 30 centimeter. So, one is the case of top pouring, another is the case of bottom pouring. We know that in case of top pouring the velocity will be here constant. So, the time of pouring will be basically depending upon the velocity here, and this velocity here at this point will be basically under root 2g into height of the molten metal which is available here. So, in this case velocity of molten stream entering into casting cavity. So, that will be root 2 g into this 14 2 g h. So, 14. So, g can be taken as 981 centimeter per second square, because this is centimeter. So, that can be taken. So, time of pouring will be basically volume by area of the gate into this velocity. So, time of pouring will be volume of casting by area of gate, that is given into this velocity of stream, molten stream. So, this you can find it, and that will be volume, you know that 60 into 30 into 14 and divided by area of the gate is given as basically it is given as 6 centimeter square, and then you will have under root 2 981 into 14. So, this can be computed out and find the results. So, this is coming out to be 25.3 seconds. So, this is the case of top pouring. Now, if you go to bottom pouring, in the case of bottom pouring, as we had studied, the time of pouring is, in case of bottom pouring, the time of pouring is equal to am by ag into basically 2 by root 2 g. So, that is how it comes root 2 by g, and then the term comes as under root st minus under root st minus hm. So, that comes as under root ht, because in this case the ht is 14 and hm is also 14. So, you have here st as 14 and hm as 14. So, this term vanishes. So, you can find directly from here. Now, area of the mold is 60 into 30 and area of the gate is given as 6 centimeter square. So, these values are known to you. So, that will be 1800 by 6 into root 2 by 981 into root ht. So, ht is 14. So, if this value is computed, this value is coming out to be about 50.6 seconds. So, what we see is in the case of bottom pouring here, the value is about 2 times that in the case of top pouring, and you can find these values quite okay. Whatever that can be different, in that case it will be different. So, this way this values can be computed. Next question is that in the figure it is shown that you have a riser. Along the riser it is shown. So, there is one riser which is also to be filled. So, as you see that you have the liquid metal, it is going through the down sprue, and in the bottom it has, so using the top gating it is filling the mold cavity, and using the bottom gating basically again it is filling the riser. So, you have a mold along with the riser for casting a plate, that is 20 centimeter by 20 centimeter is the plate. So, its cross sectional area is 400 centimeter square and its height is 5 centimeter, and then you have again the riser. So, riser is of 15 centimeter diameter. So, that is a cylindrical riser, and the height is shown as 18 centimeters. So, as you see that all the dimensions are shown. Now, the thing is that you have to find the area Ag, so that mold and the riser can be filled within 10 seconds after the down sprue has been filled. So, what we see here is that you have a condition where certain part is to be filled using the top gating and certain part is to be filled using the bottom gating. All the other dimensions are given except Ag. So, simply you have to have the expression and you have to equate it to about 10. So, 10 seconds is the time. In that case you can find the total values. So, suppose here for question 3. Now, in this case, since the mold part is filled using the top gating, so for mold part T mold, this will be volume of the mold. So, 20 into 20 into 5, that is 2000, and then it will be divided by Ag, which is unknown, and then the velocity is 2 root 2 gh. So, this will be 2 into g is 981 and h will be basically 18. So, it will be 2 into 981 into 18. So, it is coming out so this comes out to be 10.64 by Ag. You can compute these values and you get this value. Then you find the time for filling of the riser. Now, in that case it is a bottom gating case. So, this value for T for riser, time of pouring for the riser, again you will find Am by Ag root 2 by G and then root Ht minus root Hm, Ht minus Hm. You have all the values given. So, Am is nothing but 20 into 20. So, it will be all the values given 20 into 20, then by Ag you have to find, then you have root 2 by G and then root Ht. So, Ht is 18 So, root 18 minus, again you have height is same. So, this term will vanish, this will vanish. So, it will be root st. So, you can have this expression as 33.8 by Ag. So, this is how you get these two expressions. Now, the total time of pouring will be basically summation of the two. So, that is how you sum it. So, 10.64 by Ag plus 33.8 by Ag has to be equal to nearly 10. So, from this condition you can find Ag, and Ag is coming out to be about 4.44 second, 4.44 centimeter square. So, this is how you can find the area of the gate, which will take basically about 10 minutes to fill the whole casting as well as the riser. So, these questions can be solved in that fashion. Now, the time of pouring for the riser side, so that will be Am by Ag root 2 by G and then root St minus Hm. So, in this case Am is area of the mold, and that is basically a 15 centimeter diameter cylinder. So, it will be pi by 4. So, Am you know pi by 4 into 15 square. So, that is your Am, and then it will be under root 2 divided by Ag you have to find, and then you have root 981, and then this will basically vanish because St is equal to Hm. So, you will have root St, and St is basically 18. So, root 18. So, that comes out to be normally 33.8 by Ag. So, this is the time of pouring for the riser portion. So, total time of pouring will be 10.64 by Ag plus 33.8 by Ag, and this condition is given as it should be maximum 10 seconds. So, within 10 seconds. So, if you take that as 10, then in that case you can find the value of Ag as 4.44. So, this area of the riser can be calculated for such conditions. So, such problems can be solved in this fashion. You have the top pouring as well as the bottom pouring. So, in that case you can find and you give the conditions satisfied. Next, we will discuss the problems related to the riser of different type. So, let us say by different methods we will try to solve such problems. Now, here the question is given as that you have to determine the dimension of an optimum cylindrical riser attached to the side of a steel plate having plate casting having dimension of 25 by 12.5 by 5 centimeter using Keynes relationship. So, as you know that A, B and C value is given, and you have to find the value of the diameter of the riser using the Keynes method. So, what we see that in the Keynes method you have to find the x and y, and you know that the equation is, so question 4, equation is x equal to a by y minus b plus c. A, b and c values are given, and a is 0.1, b is 0.03. So, it will be 0.1 by 0.03 plus c is given as 1. So, this is the equation in which you have to fit in. Now, in this case your casting is dimension is given. So, you have to find the SA by V of casting. So, casting dimension is given as 25 by 12.5 by 5 centimeter. So, you can find SA by V of casting and SA by V of riser. For riser you have to tape that shape, cylindrical shape. So SA by V of casting you have to find, so that will be 2 into LB plus BH plus LH, so that will be SA, and then V will be 25 into 12.5 into 5. So if you find the SA by V of casting, it is coming out to be 16 by 25. So that you can find it by like 2 into 16, 25 into 12.5 plus 12.5 into 5 plus 25 into 5. So all that will be SA, and V will be 25 into 12.5 into 5. So that way you can find the V. So that way you get SA by V of casting. Now if you take the riser whose all the ends are basically both the top and bottom end contribute in the heat transfer that way. So and H is given as D, it is written that H is written as D. So for SA by V of riser will be 6 by D. So SA by V of riser will be 6 by D, because both end is, so that way you can see that the SA will be pi by 4 D square into 2 plus pi D into D. So that way it comes out as, how you can say, pi SA will be pi D square plus 2 into pi by 4 D square divided by volume, that is pi by 4 D cube. So this will be 6 pi by 4 and this will be pi by 4, and here D is more, so it will be 6 by D. This comes out to be here. So this way you can find SA by V of riser for a cylindrical riser with all its ends contributing towards the heat transfer conditions. So what you see is the on the x dimension, the x value, that is freezing ratio, will be SA by V of SA by, you have to find the SA by V of the two values, SA by V of casting to SA by V of riser. So that is 16 by 25 divided by 6 by D. So 16 by 25 into D by 6. So it will be 3 and it will be 8. So 8 D by 75. So that's how you get this x values, and further you have to find the VR by VC. So that is Y. So Y is basically VR by VC. Now in that you know that D is pi by 4 D cube, and then the value that is for the casting, so you will have VR as pi by 4 D cube, that is the volume of the riser, and volume of casting will be basically you have the casting dimension is given, so it will be 25 into 12.5 into 5. So this way you will have this Y term, and once you have this term, so that will be pi D cube upon, this will be basically 50. So 50 into 25 into 5. So it will be pi D cube by 50 into 25. So 1250 into 5, 6250. That is Y. Now you have these two values, and these two values are basically to be fit into this equation, and you have to solve it. So your equation comes out as, so it will be 8D by 75, or you can also write it as 0.32 D by 3. So whatever it be. Now if you find this, if you put this equation as like this, so your ultimate equation comes out to be x equal to, so x will be 8D by 75 will be equal to 0.1 divided by pi D cube by 6250, and then minus 1, so plus 1. And this equation needs to be solved using the trial and error method, and once you solve it using trial and error method, So, solving using trial and error method, you can find D as about 10.89 centimeter. You can solve it. So, basically what will happen, you will have to take this term out, and then it will be equation in d raised to the power 4 term, and then you can solve it. So, that is basically somewhat tedious to solve, but then you have to no other way but to solve this using the trial and error method, and you can get these values D. So, once you know D, that is what you require. The next part is the B part. So, question 3b. Now, in this the same question is to be solved using the shape factor method. So, in the shape factor method, you must have the graph for it. So, in the shape factor method, as we know, you have to find the shape factor. So, shape factor is L plus W by T. So, L plus W by T, if you look at, so L is given as, you have the values given as 25 and 12.5. So, L is 25 and this is 12.5 and this is 5. So, that is 7.5. So, L plus W by T is given as 7.5. Now, you have to go to this graph and you see that this is 7.5, and against the 7.5, if you go to this 7.5, you will have to find the VR by VC values. So, it will be here, and it will go, if you have to go straight and you come here close to this 0.5. So, if you assume this as 0.5, because it will be coming as at this point. So, from here you will have VR by VC from the graph is 0.5. And VC, you know, VC is 25 into 12.5 into basically 5. So, once you know that, you can find the D. So, basically VR will be 0.5 into VC. So, 25 into 12.5 into 5, and VR, if you take the riser of diameter D and height as equal to D. So, it will be pi by 4 D cube, that will be equal to 0.5 into 25 into 12.5 into 5. So, you can find directly D. You can solve this equation and you can find D as 9.98 centimeter. That is how, using the shape factor method, you can solve such problems. So, it will be this way you can solve it. Now, next part is you have the, assuming that volumetric shrinkage of solidification is 3% for steel, and that volume of riser is 3 times that by the shrinkage consideration alone. So, as we discussed, that you assume that the volumetric shrinkage is 3% for the steel. So, it will be volume of amount will be required is 3% of the volume of the casting. So, volume of riser which is required will be 0.0 times. So, volume of riser has to be 3% of the volume of the casting. So, 25 into 12.5 into 5. So, once you have that, you can have, so that is about 46.875. So, once you have that, as you know that you have the riser of cylindrical shape with h equal to d. So, again pi by 4 d cube, you have to compute it as 46.875, you have to equate it as that, and then you can get the value of d, that is coming out to be close to 5.64 centimeter. You can do the calculations. So, in this case you are getting 9.98, but having that kept in mind, that you are having this, no, here I think we have done some mistake here. You have to further multiply it with 3 times. So, you have to have 3 times this volume basically, because this is the amount which is only the 3% of the volume, and then further you have to have the 3 times that volume. It is written that this volume has to be 3 times. So, then you will get this riser volume as 5.64 centimeter. So, even we see that even 3 times is not enough sufficient. You need somewhere close to it using the shape factor method. So, as we had discussed that those conditions may not be sufficient, even 3 times, maybe you may have to go even higher. So, that can be seen from here. Now, let us go to next question. So, the next question is about the riser volume required for casting shown below using NRL method. So, say again the shape factor method, and in this case as we see you have a plate, and this plate basically is to be to feed 4 bars. So, as you see here the main casting is the plate, and this plate is feeding 4 bars. So, this is a case of appendage feeding, and you have the dimension of this as 40 into 40 into 8 centimeter. So, that is of the top plate. Normally plate is defined as the dimension when the width dimension is more than 3 to 4 times the thickness, then it is considered as a plate, otherwise it is a bar. So, you have this plate. So, first of all we have to find the riser requirement for this plate, and then additional riser requirement, additional riser volume requirement for these appendage volumes. So, this way you have to find the total riser volume. Now, let us see what will be the volume riser volume amount required. Let us move to now question 5. Now, in this question 5 you have the plates L plus W by T for plate, L plus W by T. So, L is given as 40 and W is 40 and T is basically given as 8. So, it is 10. Now, you go to this table again. So, against this value of 10 VR by VC, if you compute, if suppose let us say it comes here and it goes to here, so it is close to 0.4. So, VR by VC is coming as 0.4. So, VR will be 0.4 times VC, and VC is 40 into 40 into 8. So, it will be 5120, and this is the unit is centimeter. So, it will be centimeter cube. This is the riser volume required only for the top plate. Now, next we will move to basically for that bars. Now, for that bars you have 4 bars. So, the volume of these bars are 4 times the volume of 1. So, volume of 1 bar is 400 centimeter cube. So, volume of 4 parasitic volumes, appendage, it will be 4 into 400, that is 1600 centimeter cube. Now, thickness ratio, if you look at thickness ratio of the parasitic volume, that is 4 centimeter to 8 centimeter. So, that is 4 by 8, that is 0.5. So, again we will look at the this graph. Now, here you have a case of plate feeding bar, and in this case you have you can see here that this is the 0.5, this 0.5 will be your thickness ratio, and you go to this plate feeding bar case, this line, and this line it comes out to be 30%. So, volume of riser required for additional, I mean volume of the riser for feeding these appendage volume. So, for that, so additional volume of riser for feeding appendage volume, that will be 30% of 1600. So, this will be 480 centimeter cube. So, basically 5120 centimeter cube was for that plate, for this plate, and then 480 is required, 30% of its all volume will be required for the for additional extra volume for this bars which are there as appendage volume. So, once you have that, you have the total volume of the riser, will be 5120 plus 480, that is 5600 centimeter cube. Now, in this case we again see that you can find this h by d. If you have the h by d ratio is given as 0.5. So, you have h by d as 0.5. So, pi by 4 d square h can be computed out to be equal to. So, you have pi by 4 d square h has to be equal to 5600, and h by d is equal to 2, that is h equal to 0.5 d or d equal to 2h. So, if you put that, you get basically the value, if you calculate, d is coming as 24.24 centimeter. You can compute these values and you can get to that. So, you can have, so once you have d is 24.24, in that case h will be 12.12. So, this will be the size of the cylindrical riser which will be required to feed such casting. So, this is how you can solve such problems. You can see another problem of just a problem where this it is written that using Kane's curve, whether you can say that a cylindrical riser of 4.5 inch diameter and 4.5 inch height will be able to produce a cubical shaped casting of edge 4 inch. So, again here you have the A by V of casting you can find, and A by V of casting will be 1.5. So, you can find for them A by V of casting will be 1.5. It will be A by V again 6 times and then 6 times the size is 4 inch. So, 6 into 4 into 4 by 4 into 4 into 4. So, that is 6 by 4, that is 1.5. Now, A by V of casting is known, A by V of riser will be 6 by D. So, you can have, so cubical you have the riser, cylindrical riser of 4.5 inch diameter and height also 4.5 inch. So, you will have A by V of riser, it will be 6 by D. So, 6 by 4.5. So, it will be 3 and 4, 4 by 3. So, A by V of riser and A by V of casting you can find. So, you find the freezing ratio now. Freezing ratio will be A by V of basically casting by A by V of riser. So, that will be, so freezing ratio A by V of casting by A by V of riser. So, 1.5 by 4 into 3. So, 4.5 by 4, 1.125. Now, you have to look at this table. So, if you see the 1.125, you need something like volume of the riser and volume of the casting ratio as some value here from the table. Now, volume of riser by volume of casting, you have to find the ratio. If you find the volume ratio, volume of riser by volume of casting, you can calculate. Volume of riser will be pi by 4 d cube, because d and h is same, and then similarly you have the casting 4 cube. So, pi by 4 into 4.5 cube divided by 4 cube. So, this value you can calculate, and this value comes out to be 1.12. Now, if you see from the table, what you see that this value of 1.125 you got here, and then if you go, it is well above this value. So, this value is well above the line. This you are coming out 1.12, which is here. So, this is well above this line. It means you are going to get a sound casting. So, this can be inferred by looking at these values. So, you can see that from 1.125 it will be somewhere here. Normally this volume of riser will be close to 0.83 or 0.85, but it is, since in this case you have volume of riser by casting is coming out to be close to 1.12, which is quite higher. So, in that case you are likely to get a sound casting, not a shrinkage casting. So, this is where you can solve different kinds of problems in the case of gating and risering. Hope you understand it well and you practice more and more problems based on this. Thank you very much.